thanks everyone for coming. So this is the second sort of core hours session as part of our pre-application workshop for an I&I program on mathematics for social good. The idea for today was to just have a few talks as kind of starting points on a few different subjects that we imagine will be relevant to what could be included within the program. And I've asked people, mostly at short notice, so I'm very grateful for the people who are speaking, to say something about some of those contexts in a fairly informal way. So I'll try and keep an eye on the chat. So if you want to, and on the participants list, so if you want to ask a question, either just butt in or raise your hand or put it in the chat. And essentially, yeah, we'll have hopefully some short talks from each person on each of these topics, and then some questions and discussions. But I think I will, assuming that we do have all of our speakers, I'll be fairly tight on time. I appreciate people have to go, but if things finish early, we'll roll on to the next thing if we can. Okay, so first speaker, who's in New Zealand, is Oliver McLaren. He's going. Well, would you like to take it away and you can tell us what you're doing?
Yeah, sure.
Thanks so much.
I can share my screen. Cool. Can you see that?
Yeah, great. Yeah, if everyone else could mute themselves as well while the people are speaking, that'd be great. Thanks.
Cool. Yeah.
And just before you start, Megan, are you there? Could you start recording as well, please? Would that be possible?
Oh yes, we've been recording for a couple of minutes.
Fantastic, great. Yeah. All right, take it away. Sorry.
Cool. All good. Yeah. Thanks for inviting me along via Ruth. So my understanding is I've been asked to say a few words about identifiability and individual or agent-based models, as they're also known. And yeah, just kind of outline, I guess, some of the key ideas and maybe what are some, interesting research directions related to individual-based models. So big picture, I'm going to first, just give a general idea of what identifiability is in general, and then talk a bit about individual-based models specifically. So the kind of context for many people across many different fields, mathematical modelers, engineers, physicists, biologists, we typically, you do your courses, you learn how to construct a model starting from your inputs to your outputs. You learn, you make your assumptions, like maybe it's a diffusion equation, that's my mechanism, I got a diffusion parameter, or maybe it's interacting people, whatever. You get your inputs, you pass that into a model that typically you solve numerically, you simulate, you get your outputs. So a lot of, I guess, traditional applied math and related areas operate in that sort of forward direction. You inputs to outputs, you simulate your model. Increasingly, historically, a lot of interest in going in the inverse direction, but I think increasingly people are trying to integrate data and mechanistic models. So things like individual-based models, but also, ODEs, PDEs, going from data to parameters. So, or, more generally, the mechanisms, the models, the hypotheses themselves. So identifiability is really about this kind of connection between that forward direction and that inverse direction. So in particular, what conditions can you put on that sort of forward model or that forward simulation mapping that guarantee you can then go in the reverse direction? So, from parameters to data, you can have fairly arbitrary models, but can you place some conditions on that mapping, that sort of forward simulation, in order to go in the reverse direction? So the absolute minimal version of identifiability is in some ways kind of trivial, or seems pretty straightforward. It just says if that forward mapping is one-to-one, so if all your input parameters, distinct input parameters give distinct outputs, then makes intuitive sense at least, and you can sort of prove it mathematically that you can go in the reverse direction. You can go from outputs to inputs. So at its most simple, that's what it means. Under what conditions can you invert that mapping? But this idea, I guess, comes up in a variety of different application areas. People use different types of models. So people in inverse problems, systems biology, statistics, causal inference, they all use the term identifiability. Do they use the term in the same way? Does it matter what kind of model it is? All these kind of questions. So these sort of complications, does the type of model matter? So for example, I think this interest group is interested in agent-based models, individual-based models, and usually they're stochastic, for example. So does that kind of model matter from one perspective, from the formal perspective. So can you still formalize the same idea of identifiability mathematically? Spoiler answer is yes, we can. But can we efficiently implement identifiability analysis in practice? I guess the spoiler alert is question mark, question mark. It depends, right? It's a lot more complicated. In particular, I think individual-based models are the kind of models that really push the boundaries of sort of being able to actually implement these ideas. So, but we can still formalize them. So I would argue at least we can. Maybe not surprisingly to many people, the field of statistics is a pretty good area to formalize this idea of going from data to parameters. Some people think, you can't use statistics to do, say, causal inference or these kind of things. It depends on your view of statistics. If you think about it just as regression models, then that's probably true, but there are, fairly general ways of thinking about statistics that allow you to go from data to parameters with a PD, an OD, and individual-based model. So, we put some kind of details in this preprint about, various ways of thinking about it in a fairly abstract way, give a pretty general definition of identifiability. But short version is you can define it pretty abstractly from, fully specified models, parameters, all your parameters, all your initial conditions, everything, you put that in your theta. It's a big vector, or maybe it's an infinite dimensional thing, and it maps to some kind of output. You can deal with the complication that, of stochastic models by, instead of saying it's a mapping from parameters to, single valued, like Y's or D's or whatever, to a distribution over those observations. And then it kind of returns you back to it being, it's a deterministic mapping from theories to probability distributions. So it's fine. And so then the formal definition, again, of a full parameter being identifiable is just distinct inputs give distinct distributions over observables. Nothing complicated there in that sense. A more interesting in practice definition, I think, is typically you can have the case where a full model is not identified. Maybe you can't estimate every single parameter in your model, but you can estimate some subparameter or some combination of parameters. So, a classic example might be some rate parameters in a differential equation. Maybe you can't estimate them uniquely individually, but you can estimate maybe a ratio of two parameters. So there might be some combination. And so you can give a definition, sort of a more interesting extended definition of identifiability for interest parameters or combination of parameters. Here's a fairly abstract looking picture, but again, up on the left, we've got a space of all our theories. Every one of those elements in there is a fully specified model, so you can run it forward. It's an individual-based model. They all run around, interact with each other. And if it's a stochastic model, your output is a distribution over some kind of observables. So this is actually an example where the full parameter is not identifiable. So in particular, the models labeled by θ2 and θ3 give the same observable consequences, right? So that's not a one-to-one function from those two parameters, from that parameter space to those outputs. But it is actually identifiable. There's a subparameter, Q, or a query, or an interest parameter that is identifiable because if you look at the formal definition, distinct subparameters have to give distinct outputs. And so every distinct pair gives a different output. Doesn't matter that these two give the same output or are related to the same output because they're not distinct. Anyway, basic idea though, again, it might be something like maybe it's a set of rate parameters. It might be that as long as your Michaelis-Menten parameter is different, you get a different answer. And it doesn't matter that you can't identify your K1s and your K-1s individually. So again, this is kind of just high level mathematical abstract idea, but there's some conditions on that forward mapping, regardless of what kind of model it is, that tell you that you can go in the reverse direction. But implementation might be difficult. And in particular, that's relevant to individual-based models. So I've been part of a modeling team doing work for the government on the COVID response, and that's involved building a lot of models of infection spread through New Zealand, which thankfully is not so bad. But one of the models that we've been building is a big 5 million individual model of spread through New Zealand. And you would say, one full set of parameters for that model is one fully specified model. So that's one full set. What kind of output do you get? Well, you run that forward, and maybe your observable is the total infected and recovered individuals. And you get a distribution over those outputs, again, because it's a stochastic model. So one parameter gives you one full distribution, which, key point from an implementation point of view, means for one full model configuration, you have to do a whole bunch of runs, which is expensive. So again, leads to this idea of implementation issues. Basically, you have these expensive and simulation-based models. So you can't write down an explicit, a statistician would say like likelihood function or whatever. You've got to do it by simulation typically. So you've got to run a bunch of realizations. Almost certainly, if you're dealing with these large, complicated models, there's going to probably only be at best partial identifiability. You're not going to be able to identify all parameters. And I think that's something that's still not appreciated enough and addressed enough. Also, another issue is high dimensional model output. So an ODE, usually get maybe like one trajectory over time, scale a number over time. That's fairly easy to deal with. Output of an individual based model might be the positions of 5 million individuals over space and time. So just dealing with that output is also, it's a distribution of a high dimensional output. The traditional way to deal with that is to do things like summary statistics. So ABC, synthetic likelihood, typically try and summarize that. There's increasingly, I think, definitely interest in dealing with the high dimensional output sort of as it comes without doing summary statistics. So using things like neural nets and machine learning to handle this high dimensional output rather than have to reduce it to a summary statistic. So again, just says the same thing. You just need to run the model a lot for every parameter value. It's probably not going to be one-to-one in the full parameter, and you have these high dimensional values. So key research areas that people are interested in are, again, about doing approximation and emulation of these models. So instead of having to run your model over and over again, and also trying to approximate your output as some low dimensional summary statistic, let's approximate the input to out, the parameter to observable mapping by a neural net or something like that. And so that's a big topic at the moment. And I would say one of the main arguments for doing it with something like a neural net is the argument that they can deal with that high dimensional output rather than having to reduce it to a summary stat. Again, when you're doing something like real world stuff with COVID or whatever, you're getting a lot of different data sources, and just being able to actually synthesize that systematically in order to overcome those identifiability issues is a big thing. And like I said, I would say really just facing up to the idea that we're probably not going to be able to identify all the parameters based on available data, but how can we identify some parts of that model? I think that's a big open topic. Few other things. So identifiability is a fairly idealized concept. It's sort of, if you've got a data distribution, but it's a sort of a perfect data distribution. But in reality, we only have a finite number of samples from that data distribution. Can make a big difference if things are, sensitive. Just because it's identifiable doesn't actually mean you can estimate it in practice. Also, the model's wrong, classic story. But how do you deal with these things in the context of, wrong models and all this kind of thing? So identifiability is a formal condition that sort of assumes your model's correct and you have access to the full distribution. So there's a whole bunch of other topics that kind of come under that general umbrella, but go beyond pure mathematical identifiability that are of interest. So that's kind of a rapid fire overview of this topic. Not sure if that's at all relevant or interesting, but thanks.
Thank you. I don't know. Thanks very much for speaking. Yeah, I think that was really helpful. Thank you very much. I mean, I certainly have some questions, but I think it would be good to hear from other people. If anyone else wants to ask a question, if you want to raise hands, I think if you go to the participant list, and then I think there's an option there to raise hand. Okay, Peter, I think Peter Challoner. Do you want to unmute yourself?
So, as a Bayesian statistician, prior information interacts greatly with identifiability, in that if I have a prior specification and the parameter is non-identifiable, then really I just don't modify the prior.
Yeah. So, I mean, from a Bayesian point of view, you would say, Well, the best case, you know, in the idealized math world, is your prior just doesn't get updated. I think in practice also, though, there are issues like, you know, a bunch of MCMC algorithms and, you know, these kind of things can definitely have issues in the presence of identifiability. So they, you know, when these kind of regularity conditions fail, they can definitely struggle to even return you that, the fact that your prior is unchanged. I've definitely had non-identifiable models, you know, get stuck in some region of the parameter space and this kind of thing as well.
No, I'm not saying it's, it's a panacea, but it's a different way of looking at identifiability, in that it's not that the parameter is not identifiable and therefore you can't get at it, but the model or the data doesn't tell you anything that you didn't.
Yeah, the conclusion is it's uninformative, right? The model is uninformative.
Yeah, absolutely. And I mean, so there's a few different, I mean, I, you know, absolutely agree. So, I mean, you know, if you put a prior on a non-identifiable parameter, you do crank the handle. Ideally, again, you know, assuming everything kind of goes correctly, you'll just get your same prior back and it won't be updated. I think there's a lot of interest for people, for some people, I guess, in saying, okay, but like, can this data actually tell me about this parameter? Like, structurally, it's a sort of a structural question. Is it possible in principle to learn from the data, or am I, you know, just going to get my prior back? And I would say, I mean, even a Bayesian would probably say the sort of the information from the data comes from the likelihood. And so it is kind of a question about the likelihood as opposed to the prior, in the sense that, you know, if the likelihood is not informative, it's not going to update your prior. So you can kind of get away with looking at the likelihood function in many ways, I think. But
we've got a few other questions, so I might just butt in if you don't mind. And Gesine, I think sorry, I wasn't. Do you want to go next? I wasn't.
Yeah. Okay. Yeah. Thank you. I think it was an inspiring talk. Thank you, Oliver. There are lots of things to discuss. I just wondered about the connection with social good. If there are some, so you mentioned the example of COVID-19, but are there some other sort of examples which we could include and sort of tackle to? Because sometimes it's good to think of concrete examples in order to try things out.
That is a great question, and I'm aware that this is a program related to social good. As a person joining last minute, I'm a little bit unaware of the general, you know,
don't worry too much.
Applications, but yeah, I mean, I would say, yeah, for example, I mean, it's a big question when we're dealing with these big COVID models and stuff like that.
Are there any nice ecology examples you can think of, or I don't know, from biology, or, you know, which are more individual based rather than like, you know, modeling of tumor or something like that? Any things like that you're aware of?
Wait, so modeling a tumor, like, is a
no. I'm saying I was saying, could you think of any? Do you know of any examples that might be relevant in biology or ecology? But I wanted to exclude the kind of PD models, you know, PD continuum models in biology.
I mean, absolutely. Just, I mean, so in general, I guess the idea, and I mean, this comes back to, you know, what Peter was saying as well. I mean, depending on who you're working with, right? I guess some scientists who do the experiments or do the field work, one question they have is it possible for me to estimate this by this parameter or this concept by collecting data? And so anytime you have something that is, you know, not directly measurable, but is linked by a model. So, you know, you collect measurements on something, but it's linked by a model to some parameter of interest. And absolutely, these questions come up in ecology and ecological modeling. I mean, actually, ecology is a great area where people have been synthesizing models and data for a long time. I mean, you know, there's that, was it a book or the paper, the like wider population cycle and those kind of things. I think you can definitely sort of phrase those sorts of questions as identifiability questions. I mean, yeah, it's such a, again, it's a sort of a mathematical concept. So I guess if you want to apply it in a context, you know, you've got kind of free reign, but that also has the downside that it's not strictly a social good concept, right? It's a can I link some unobservable thing to some observable thing? And so I guess there are examples in ecology where, you know, you're taking indirect measurements almost always, right? And you want to know about something that you can't directly observe. Is it possible to estimate that thing that you can't observe from these kind of measurements? And again, you know, like Peter was saying, maybe there's a different type of data that if you went and collected it, you could identify that parameter. But I'd leave it up to the subject matter experts to sort of make those links, I guess.
Is that right? Is that right, Yassine? Or do you want, I don't know. No, sorry. You're on mute.
Sorry, yeah, that's fine. Thank you.
Great,
yeah.
Thanks. David, I think you had your hand up next. Do you want to say something?
Yeah, I was just thinking about the social good question. I mean, I think one of the things that we've been discussing during the week is the fact that there's all these policy advisors giving advice on the basis of models. And so one thing that we'd like to say is, well, wait a minute, these models have all these faults in them that you just can't be making the claims you have just because you've got an incredibly complicated individual based model of something. It doesn't make it more true. Richard had this nice phrase that he talked about yesterday. You should say it first, Richard. I thought it was like truth laundering or something, or what was it? Model laundering. You don't know what to say to a policy advisor. You put everything through a model and then suddenly it sounds very true. And you would be able to, I mean, that would be the social good you would be offering is a kind of counter to that type of thing.
I mean, absolutely. Like, again, I mean, I probably shouldn't say too much, but, you know, we are writing modeling reports for government based on, you know, very complicated models with very questionable, you know, I mean, all models, right? But, you know, questionable assumptions in various places. And are these parameters identified? We don't know, you know, to what extent is this actually a reliable policy advising tool? It's, you know, we put the caveats in, but the people who they hear model and they hear this is what the result was and they think, cool, that's my policy decision. And I mean, this ties in too with, so in the area of so-called causal inference, identifiability is another, you know, it's a big topic within causal inference. And again, you know, depending on who you ask, but I would argue you can subsume that concept of causal inference identifiability within this kind of same framework. And so you could say, what is the effect of this policy? Like, can I identify this policy intervention effect? So you could say, you know, you've got a model of, I don't know, again, some kind of social system or something. And you say, if I intervene on schools or educational policy, is this effect identified or is it confounded by these other variables, this kind of thing? So definitely from a policy point of view, identifiability of these sort of causal effects is probably pretty important.
And this then relates to what my real question was like this thing where you make an IBM and then you use a neural network to approximate it in order to, I mean, to me, that just sounds like evil, because basically you're constructing, this is sort of a double laundering. You're constructing a model you don't understand, you're running it, and then you're getting the neural network to sort of mangle the output to tell you that you've understood it. And each time you've done that, you'll have kind of said, well, I'm using even more advanced techniques now.
Yep.
And then the answer will be, I don't know, wear masks or don't wear masks or something. And then everyone will go, yeah, and we don't need to wear masks. And we'll all be happy because the model said it and the neural network said it.
Absolutely. I mean, a few things. I guess I can get away with not doing that a little more because I'm in New Zealand on the other side of the world, not in, you know, Oxford or Harvard or MIT or whatever. They have, I mean, I was talking to a postdoc who, you know, I knew when he was a PhD student who's in America now, and everything is use a neural net to approximate this physics model or this whatever, you know, and he doesn't believe the results, but it's what everyone does. And there was a nice paper recently by some people in the Google research team on, I mean, it is identifiability. They called it under specification. Exactly the same concept, but basically under specification presents challenges for the credibility of machine learning or something like that. Yeah. And they present a whole bunch of examples where basically having these underspecified or you know, partially identified models presents a lot of challenges when you try and apply them in a new context. So they might seem like they do well, you know, within sample, but if you go to a radically different context, the fact that you don't know that mechanistic parameter means you can just be wildly off.
Yeah, and I think that ties into another thing we said about social good. So basically, Google have employed all these people to reinvent the word identifiability and apply it to loads and loads of neural networks. And then their first example was an SIR model, which everybody has known for a long time. So that comes down to social good because they're not paying tax properly. And instead, they're using they're using this as an excuse that they're doing good research, while actually they're doing sort of substandard research and hyping it up in the newspaper. So that's my take on where your research comes into social good.
Yeah, I mean, absolutely.
Thanks. Yeah, there's lots of really good connections there. Richard, do you want to squeeze in a quick question?
Yeah, I just wanted to focus a bit on the sort of your practical experience. So I mean, you had a nice slide at some point that said sometimes you can't infer this parameter, but you can infer this Q, this query, or this sort of some other representation of the parameters in the system. And that may be what matters. So I'm wondering, you've obviously worked on COVID, and that's very important. How often do you get into a situation where you showed, like, you know, different models giving similar predictions, and then you can't tell between them? But the flip side of that is, of course, they may essentially make the same predictions all the time.
Yep.
So how often do you get a situation where you can't identify the model based on what you've seen so far, but there may be radically different predictions in the future, so it really matters which model is right?
Yeah, and I mean, that's exactly the you know, that's the kind of the flip side, right? The flip side to identifiability is, and like non-identifiability is to say, well, from a prediction point of view, which, you know, all the machine learning people talk about, it doesn't matter, I can't identify this parameter because it gives the same prediction. But that's the big thing is when you're trying to generalize to new circumstances, right? And I mean, yeah, every kind of model that I deal with, it, you know, it matters. That parameter matters because it's in a mechanistic model, and I know that I can make an experiment, or I can, you know, be dealing with a real world situation where if that parameter is changed, you get radically different, you know, radically different predictions. And so, I mean, you know, we absolutely deal with that all the time. And I mean, that's the whole argument for why we still deal with mechanistic models in the first place and not just do pure prediction. But I think it's interesting, despite the fact that it's a very, you know, hypey paper with SIR models as the first thing. I mean, the fact that even the Google engineers will admit that it matters from a pure sort of, or machine learning point of view as well is interesting. So, I mean, it matters from their practical experience. I mean, yeah, I can't think of an application where it doesn't matter, right? It's more just any different, if it's a different treatment or it's a different scenario, it's got to be a qualitatively different scenario, but absolutely, you can get wildly different predictions from things that are non-identifiable for some set of data, but, you know, they give wildly different predictions about a qualitatively different regime.
Thank you very much, Oliver. I'm going to draw a line under this just in the interest of keeping to time. Thank you very much. It was really interesting, really stimulating, and it's been really nice to see like a totally independent party link up the things that we've been talking about. So that was really good, and it's also brought a few ideas. So I think the next, thank you very much. Please stick around if you can, but I appreciate that you probably want to go to bed. So, everybody,
I'll subtly drop off.
Yeah, no worries. Thank you. So Michael, I think you're up next. Is that right? Yeah, great.
And thanks for your flexibility with the schedule.
No problem, no problem.
I just mixed up time zones horribly.
Don't worry. Thank you. Thank you for speaking. So, right, I will let, do you want to share your screen, or are you?
Yes, I'm trying, but that should do it.
While you do that, just as a quick, I did actually have a couple of questions for Oliver, but I'll aim them at you at the Slack. So please do join up, and yeah. Okay, Michael, go ahead.
Do you see my slides?
I can certainly.
Oh, very good. So, so my background is in sociology and economics, and I'm interested in dynamics on the internet in general. So processes of opinion polarization on Twitter or Facebook, the spreading of fake news in these systems, things like this. And I use agent-based modeling to understand these systems, to generate testable hypotheses, and then I gather data and conduct experiments to test them. And I will talk about a little about one or two models here, and perhaps these are actually candidates for to be where we can apply the methods that we've just been introduced to. So what I was trying to think about is how to motivate in the proposal why we need more mathematical modeling. and in particular mathematical models of social problems. And here are some thoughts and some examples. I think a strong argument is that that societies are just becoming increasingly complex, and there are some parts of this complexity or some sources of complexity that we already understand pretty well. So there's a lot of research on the individual level. If you look at what social scientists are doing, there's a lot of research on how individuals respond, how they act on the internet, how they update their opinions, how they share information online, for instance. There's also a lot of recognition of all this complexity arising in machine learning. Yeah, these systems are black boxes and we don't understand them, and people are investing a lot into better understanding this complexity. But there's one source of complexity in these social systems, in these online social systems, that we are only starting to understand, and this is the social complexity arising in these networks. And this arises because the users in these systems do not act in isolation, but they respond to each other. Yeah, this is what we are. So this is one of the reasons why we go online. We can interact with others. We can communicate new information. We can get new input, update our opinions. And this can give rise to unexpected emergent phenomena, and very often also undesired phenomena that we first need to understand. So here's an example I want to give you, and it's something that we came across rather recently. And it started with puzzling empirical observations. So if you look at the research on the effectiveness of social bots in terms of how effectively they spread their messages, you find seemingly contradictory things. So on the one hand, we see that there are just many bots out there. We see that, so for instance, I think in the 2016 American elections, the presidential elections, they found more than 400,000 bots only in the political realm. However, most of these bots are communicating with other bots. So bots have very few human followers, which seems to be good news. On the other hand, we also see that sometimes the content generated and communicated by bots can spread very, very far in networks. So even though these bots seem to be rather unimportant in terms of having very few followers, they can be very successful. They can have a big impact on the dynamics. So how is that possible? And the explanations that are in the literature are very much focusing on individual characteristics. So for instance, it's argued that the content that these bots are emitting is just very attractive to humans. Yeah, it's the stuff that that is mind-boggling, that is new to us. Very often it's new to us because it's just fake, it's just false. But this seems to be stuff that that is attractive to human users. There's also a lot of research on what individual characteristics make you more likely to consume and share bot news. It turns out that people who score low on analytical skills are more prone to consuming bot content. Also there seem to be some effects of political orientation. Yeah, so there's research on this, and people try to attribute these or try to explain these puzzling empirical findings with psychological variables. But I want to show you, and I think it's possible to show that there's also a part of this story could also be related to the social complexity. What I'm showing you here is, now I have to move you away, is two ideotypical simulation runs with Axelrod's model of cultural dissemination. For those of you who don't know this, it's he's setting up a cellular automaton. I do it here with networks. I think it's a little more than 100 agents here. Each of these agents is described by 5 nominal characteristics. So these are, you could call them opinions. It's stuff they believe. So for instance, this could represent whether they what they believe is the cause of the COVID virus. It could be, one trait they could adopt is that they believe it emerged in Wuhan on some market. Other agents might believe it came from a Canadian lab that made a mistake. So there are all these different theories for that. And we are kind of modeling here for each agent, what is the theory that they consider most plausible. Yeah? Agents are described on 5 of these, on 5 different dimensions, and there are 10 possible traits that they can adopt. And this is exactly what Axelrod was modeling. The only thing that we added is this bot in the center here. And we are manipulating how much ties these bots have, so how much followers these bots have, and how active they are. Active in terms of how often they are communicating their traits. And we gave these, all these agents got at the beginning, like in Axelrod's work, a random set of traits, a random set of beliefs. Also, the bot got a random set of beliefs, but there was one belief that only the bot had. And what we wanted to know is, in equilibrium, how many agents have adopted this bot trait. The bot itself is only communicating, it cannot be influenced by others. Oops. Can you still see my screen?
Yeah, I can still see it. Oh, okay. Yeah, it's playing. It's playing. That's good.
Good. I just have to. So look at the little animation on the right. It's a bot with many, many links, and it's a very active one. So in 75% of the iterations, the bot is communicating and not the other agents. So I'm running this now. Yes, there you go. And what you see is that this bot is having many strong ties. So you see these thick lines. It just means that the bot is able to attract, to convince many of his followers, and they totally believe what that guy is saying. So they grow very, very similar. They adopt all the bot traits. But right now, you're also seeing that there are many agents who are leaving that network. Yeah, who are not believing anything the bot is communicating, and this is also kind of the outcome here. So at the end of this run, 35% of the agents adopted this bot trait. Now let's move to the weak bot on the other side, on the left. This guy is connected only to 10% of the agents and is much less active. He's communicating only in 10% of the iterations. And you see that this bot is generating a very different dynamic here. He is not very quickly attracting all of his friends close to him. Now he, however, has established close links to his friends. But you see that the other agents are not moving away. Of course, there are always a few that are not attracted. But if you look at the network now, you see that the weak bot, the bot who's having fewer followers and who is communicating less frequently, is spreading his messages way more efficiently than the guy on the right. And the reason is the following: if you are a very aggressive bot, then you very quickly attract or convince some of your followers, and they grow very similar to you. The problem is that those guys become very similar to you, but they also become dissimilar to their friends. And as a consequence of that, their friends don't listen to these individuals anymore. However, if you are a weak bot, then you from time to time communicate your message and people will listen to you, but they don't very quickly grow so similar to you that they lose contact to their friends. And as a consequence, the bot can indirectly still influence the friends of his followers. And that's a very robust finding. We don't only see this in Axelrod's model, we see it basically in every model that combines social influence with homophily. Homophily is the critical force here because if similarity between the bot's friends and their friends is too small, then they won't interact with each other anymore, which is the homophily assumption. So what this example, I believe, shows nicely is that it may be true that fake news spread differently because people respond differently to them. Or it could be that there are really some personality characteristics that play a role here. But an alternative explanation is that there's just a complexity arising from the interactions between individuals. And why do we want to understand this? it's actually critical, I believe, that we understand this, because it suggests different policy implications. If you really believe that it's psychological factors that play a role, then what we typically do is we make people aware of this and we educate them, and then we try to influence their individual behavior. But here this will be very difficult, simply because the driving force are the individuals that are not even connected to the bot. So how on earth are we supposed to make them aware of this whole complexity? Or very often we try to find technological solutions. Yeah, people try to identify bots, to detect bots, and to ban them. And I'm not arguing that this is a stupid strategy, but if this mechanism is actually playing a role in reality, then those bots who are not very active are the most the most problematic ones. But those who are not very active are also those who are most difficult to detect. So rather than so for instance, if you look at this literature on bot detection, good algorithms are supposed to detect 99% of the bots. Yeah, but these could be those bots that are easy to detect because they are very active. But we actually want to detect those who are not active because they are the most, they may be the more difficult ones. So we actually need to understand the social complexity in the system in order to design it in a way that we prevent problematic dynamics like opinion polarization and the spreading of fake news. I had a few more ideas that we may want to talk about, but I suggested I leave it at this.
Thanks very much, Michael. Does anyone want to ask a question? Seeing your hand is up, but I suspect that might be because it's left up. Is that the case, or did you want to ask?
Actually, I would like to ask a question.
Okay.
So it's both is true. So because I forgot to take it down, but I would also like to ask a question. So very interesting talk. I just want to say in ecology, there are all these competition models. You've got different species. So you said that it's not just one bot. So it's thousands of bots competing for a similar market. Have you looked into that?
So we are very aware of this. The thing is, what we wanted to show here is, so for the model that we developed so far, we put in only one bot because we wanted to exclude that this effect of, so that is empirical finding. Let's start again. The empirical finding was that bots have very few followers, but can still be extremely successful. And one explanation could just be that they're only talking to each other. There are many, many bots and they only talk to each other, which is a plausible explanation. And we just wanted to add another explanation. And for the model, we therefore excluded that there may be many bots because we wanted to show that there could be an alternative one. In a realistic model, there are of course multiple bots and they interact with each other. They might also reinforce messages they are communicating, which is also one reason why they have been developed. And then also this complexity needs to be considered. So I believe what you're suggesting is another reason why we need these models.
Yeah, and mathematics actually for these models.
Yes.
Mathematics are not trivial.
Oh, definitely. Even this stuff here is not trivial.
Yeah.
And I think this is an argument that we could make in the proposal, is that there are these different sources of complexity and each of them has attracted some attention, but we actually, to make it useful, we have to combine them. Yeah. So this was one of the latest slides. The big challenge is to do this in a way that we do not create a monster. We still need a mathematical representation of all this complexity that we can handle. And for that, we just need to bring experts together. So I believe that could be a nice argument for such a workshop.
Yeah. No, I didn't mean to say what you were doing with trivially. Actually, I'm quite impressed.
Oh, no. I didn't understand it like this.
Okay.
Richard, do you want to ask?
Yeah, so I was going to say, I mean, yesterday when I was talking to some people, I crudely caricatured you, Michael, as having about 2,000 different explanations for polarization, for example, that it could be like homophily, it could be that, you don't want to talk to those who are different, or when you do talk to those that are different, they repel you so much that you go in the other direction or so forth. And what I like, I mean, which I didn't say so much at the time, is that you obviously try and do these experiments once you've got your model to say whether this mechanism is the one that's actually at play. And a lot I guess what you're trying to do is to design the right experiment that will pull out whether or not this model is correct. And I just want to say, I think that ties in very nicely with the previous discussion, in that a big question with an agent-based model like this is, what predictions can the model make that distinguishes it from another model? So we have, as I say, a number of different explanations for why you might get polarization, or why, in this case, for example, a bot might have an influence in a network. And obviously, because you have a number of different explanations that say, you get polarization by itself cannot distinguish between them. So I think there's a mathematical task to be found somewhere, which is, essentially what statisticians would call experimental design. But in a very complex model, like an agent-based model, it's not a simple case of just saying, well, what's the, I guess, maximal information you can gain by measuring a parameter or something, but it's a more complex search problem about how do I either design an experiment or decide what data I need to measure that would identify which of these models is most likely to be true, and where is the maximum divergence between the models.
Yeah. So this could also be an important point in the proposal. If you look at this literature on opinion dynamics, you have hundreds or thousands of models, and every second week I'm invited to review a paper where someone proposes another model, and very, very few people compare models in terms of the assumptions and the predictions, and this is really critical. So this is one of the things we are pushing here. So also this is one of the reasons why I took this very old model by Axelrod. I want to start with a simple model, something we've understood, and add a teeny tiny ingredient, and then later study whether it's robust also in other settings. But it's a huge challenge to compare models. First, you need to create a framework where you can compare the two, where you, in the perfect world, have just one parameter that you can move around, and you move from one model to the other. And then also the challenge is also to then to understand why the models make different predictions. So I think we succeeded here and there in this, but also that I think would be a very strong point for collaborating, for also getting expertise from statisticians, from other fields, because this is in the social science modeling literature. It's horrible. We have so many models, and very few people have an understanding of where they differ, whether these differences are critical in terms of the assumptions, and what are different macro predictions arising from these differences.
Yeah, it certainly was during my time working with data in sort of individual based models in ecology. It was the same thing, that you have a different model every week, and not very much discussion about whether these models might actually be the same model with a different perspective, or whether they ever made different predictions or so. And yeah, I'm sure David, for example, has more to say on that, as he's been working on it a bit longer than I have. But I think I can see social science going very much the same sort of direction.
But so then the question is, how did other fields solve this, or what are approaches that people apply in other fields? And Oliver, I think, gave us a talk about potential ways.
I think, my experience is, if you can if there's a specific thing. So for example, I doing my PhD, I looked at traffic models, and you'd get the same thing where people would come up with a new traffic model, they'd analyze its stability and go, look, it creates stop and go waves, and then, what my PhD supervisor did was essentially generalize those and say, well, actually, all these models, the instability is the same. So now it's, now that calculation's done. So no one needs to publish any more papers like this, because it's all the same. So yeah. One thing I want, sorry, one thing, oh, go on.
No, I just also want to say a few positive things, because sometimes we do manage to find these differences. So for instance, if you look at this literature of opinion polarization, opinion dynamics leading to opinion polarization, then we see that some of these models assume that this repulsion that Richard mentioned, that if you meet someone who's very different to you, then you hate these individuals and you distance yourself from those individuals. This can generate polarization. However, other models assume that you move to extreme opinions, not when you talk to someone who's different from you, but when you talk to someone who's similar to you, because your opinions are then being reinforced. Yeah, if I talk to someone who hates Trump, and that person hates Trump for different reasons, I hate him even more. What these both models can predict polarization, but under radically different conditions. The first model with the negative influence, if you meet someone who's different from you, they suggested if there's a lot of interaction between dissimilar individuals, we move away. And the other one says, hey, if there's a lot of interaction between similar individuals, we move to the extremes. And one implication is that filter bubbles, these bubbles that we are supposed to be trapped in, where we only interact with similars, will lead in one model to more and in the other to less polarization. So there are examples where we understand what are the critical assumptions of these models in terms of their macro predictions. And this also leads us to design empirical experiments.
One thing I wanted to say on that is I mean, Richard mentioned experimental design, and I get the impression that you have done some experimentation, but I think often with social data, you're dealing with more observation studies, right? Where you don't have that ability to be able to quantitatively test the different things you'd like to. I don't know whether any. I think Gessim's had to pop out, and I appreciate the statisticians in the conversation might not work in these sorts of areas, but it'd be interesting to know if there's anything in statistics that can allow shed light on that, i.e. how you might bridge that gap.
I mean, there's a field of active learning, which is essentially a rediscovering of experimental design, and there you have criteria like what data should I try and observe, and you can say what data would, like before if I observe the input but not the output, what data has the most distinguishing outputs for different models? So where do models most disagree? And I think there's a lot of insights that could be taken from that. I mean, so a lot of this is being done. I think what would be useful in terms of like a contribution is to say, how do we sort of systematize this in, say, the sort of context of ABMs or models of opinion dynamics or social learning or whatever we're interested in, and say, not just in an abstract sort of machine learning sense, where can I find data that's going to disagree between models, nor in a sort of formal experimental sense, but in this is the sort of model I've got, like what procedures, what algorithms can I follow in order to either generate new data that will distinguish between models or to search for data. Like, how do I even find the predictions that models make that are different? I mean, Michael talks here about these two different opinion dynamics models, and they make different predictions. And some of that can come from, either a mixture of intuition or sort of traditional thinking about the dynamics. But it'd be nice to sort of have almost a system in which you could sort of plug in your models, and it would say, you should do this, or, here's a set of experiments you could do, here's a set of data you could observe.
Yeah. I once had this discussion with Michael Macy. So I presented one of my models, and he was saying, how are you going to test it? And I said, I have no idea. And his reaction was, oh, so talk to your friends, go to the cinema, read some books, you will get an idea at some moment, which is not a good algorithm. Yes, but so that would be wonderful to have some guidance, and this could be very general, but some guidance about how to identify critical assumptions, because they will lead you to designing an experiment or looking to find those contexts of reality where you would be able to compare or to test and compare models. Something that is very controversial in the social sciences, or not done a lot in the social sciences, and I think that could be such a general guideline, is to compare models. People always propose new models. They don't compare their models. And even though even social scientists know that this is one of the basic principles of philosophy of science. Yeah, this is what we've learned from Popper, that you always have to compare theories.
That's interesting, because in sort of collective animal behavior, we've certainly been through a phase of comparing models a lot, but then you also get into another problem, which is I've got my new model and I've picked off the shelf 2 other models, and my model's better than these 2 models, according to the data that I measured. And I think, I mean, this sort of goes back to the question of how do you even use, like, how do you use your model in terms of giving advice? And Oliver mentioned at the end of his talk that your model is wrong, it's misspecified almost by definition. So, I mean, you have something like, for example, Bayesian model selection, which would say, if I've got 5 models and one of them is right, as long as I measure enough data, it might tell me which one is right. But if you've got 5 models, all of which are wrong, and you just evaluate which one gives you the highest likelihood for the data, it's not clear that process, like mathematically, necessarily leads to exactly what to give in the model that will be most useful to you, nor is it clear that any of your models is adequate.
Yep. Most likely all of them are false. Yeah.
I saw David unmute himself, so maybe he has something to say on that. Yeah, I think I just wanted to say, I mean, there's something I think there's missing in this discussion is that, I mean, whenever I speak or say anything, it's misspecified. So like every type of communication I make is underspecified, but that doesn't actually stop me from speaking. Many of you might have noticed. And so I never saw, like in the collective animal behavior thing, I never saw it as a big problem that, well, it was annoying that Richard kept creating new small variations of models I published 10 years ago, but it wasn't really a big problem because in a way we're just describing the same things with slightly different mathematical forms. So I always get worried when thinking about the program we're going to do, if we're going to set up a program to unify all models, the one model that rules them all or something like that. I always get worried about that because actually when you define a model in a paper, all you're doing is saying something about the world and making predictions about the world. And there isn't a subject, I hope there isn't subjects where if you're doing a model-free thing, if you're writing an introduction for a paper without a model in it, and another person's written a different introduction for a paper without a thing, we don't need to have a whole theory about why they wrote slightly different introductions to their papers with slightly different words with the same ideas. So I think it might be interesting. I think it's definitely an interesting thing to look at, but I'm worried about getting into that kind of like, let's try and formalize it all and make it into one thing. Or at least I think that what I'm saying now should be the sort of counter theory to the theory that we can construct one single model.
I think, I mean, you say that, for example, that, I mean, you're not stopped from speaking because what you say is never like precisely what is going on in your brain. I mean, and the same is true in models, that you have a model is, I mean, the famous saying, of course, is a model is always wrong, but some models are useful. But when we do model selection, for example, we don't measure whether the model is useful. We measure something else. We measure, for example, its probability of predicting changes in the motion of a fish or probability of predicting a certain level of polarization. And I think one thing that often isn't addressed explicitly is whether we're measuring usefulness. So, and I mean, you know, for example, with the work that you've done on international development and stuff, that usefulness is not the same as predictive accuracy in every case. Sometimes you want an understanding of a system and having a massive black box.
I've just become aware of time, and I noticed also that Peter Challoner has had his hand up, and so I think I'm going to be flexible and say, Peter, would you like to say something quickly?
I just wanted to say something quickly about model discrepancy and the fact that all models are wrong because our mathematical description of the world is not the real world. And there are ways to try to get a handle on that model discrepancy or what's wrong with the model. And I also think, you know, a lot of stuff I work with is on decision making. And if you're trying to make a decision, is the model helping you make the decision? And if you have a variety of models, I don't think we want a formal method of finding the best model, but we need a formal way of combining those models together to get the most informative, the most helpful thing for making the decision, which is not at all the same thing. it's trying to make models useful rather than make models right, because they have to write. And
that's
I think
a good.
Get away from that. The whole idea of the right model or my model's more right than yours.
That's a good point. I think we should draw a line under. I mean, I think that these threads seem to be coming back. So I think and if people feel like we need to address any of these more, please take it to the Slack group or join us later. So apologies for cutting it off. But in the interest of time, Dan, do you want to?
One thing. Thanks everyone for the input.
We should say thank you, Michael, as well.
And for the proposal, let me know if you feel that I can be helpful, and give me clear instructions.
Yeah, no problem. Dan, do you want to set up?
Yeah, sure. Let's see if I can share my screen. I've not done this before, so I'll see if see how easy it is. Which one is it?
Looks good, Dan.
Is that working?
Yep.
Do I have to put it in slide mode?
I think that probably would help.
Yeah. Can you see that?
Yep. It hasn't come up as like a full screen.
Oh, that's weird because it's full screen on mine.
Yeah. Anyway, let's not play around with it too much. Just carry on. I think it's probably I can read everything that's there, so that's the key thing.
There's a little. I'm just going to show control. I don't know.
Let's leave it. I think.
Let's leave it.
You can flick through. Go ahead.
As long as you can see it. Yeah. Okay, so a little bit of. I just wanted to say a little bit about some work I've been doing on probabilistic agent-based modeling, and a little bit of background, I guess, just to motivate it for social good. So this all started from some work I was doing on policy making, so working with policymakers with agent-based models of the economy at the time. And so it struck me while I was doing it that the problem was that what we would really like to do when we're using models to inform policymakers is really to what we should be telling them is the Bayesian posterior, really, of given some incomplete, noisy observations of the world, and given some model assumptions, then what's the probability distribution over some measure of interest that's relevant to the policy decision? And with agent-based modeling at the moment, actually nothing like that really exists. We can't, on the whole, if your agent-based model is anything more than pretty trivial, then it's very difficult to get to a true Bayesian posterior, given noisy, incomplete observations. And so what I wanted to do was to try and think about agent-based modeling right from the start, so from a completely probabilistic point of view. So then we can take into account the uncertainty in the parameters, the uncertainty in the model itself, the uncertainty in the state of the model. We often, if you've got a agent-based model of a simulation of society, we don't really know even the state of the model to start with in full detail. The uncertainty in the observations are usually aggregated, they're noisy, some of the observations might be even wrong. In fact, almost certainly are. And so how to deal with all these things. So as a physicist rather than a mathematician, it seemed to me the mathematical language of quantum field theory fitted this problem precisely, really, or very well at least. So quantum field theory deals with a large number of interacting particles in this case, but it can deal with particles that act in any way whatsoever. And so we can apply this pretty much pretty directly to agent-based modeling, where instead of having particles, we've got agents. So that's pretty much what I did. I boiled it down. So there's some things about quantum field theory that actually we don't need when we apply it to ABM. So actually it's a little bit simpler. In quantum field theory, they have this idea of a quantum amplitude, which is this complex number, which when you multiply it by its conjugate, then you get the probability. But with ABMs, we don't need to worry about that so much. We're just interested in probabilities. It's going to be quite difficult to explain quantum field theory in 10 minutes, or I've actually got 4 minutes left now. So I won't do it entirely, but I'll give you just a brief idea of how it works. So basically, you start off with just an empty state. So it's just an empty model. It's an ABM, but it's got no agents in it. And that's kind of useful because that's the universal state. No matter what your ABM is, if you've got no agents in it, then you can always start with that state. And then you just define these creation operators. So you create you have a creation operator that operates on the empty state and has the effect of just creating an agent in a given state. So using creation operators, you can create any state at all. So you add, for each agent, you add each agent in the model, you can add an agent in any state, or in that specific state to build up a state. And then basically you can add these states together. You can multiply them and add them up, and as long as they add to 1, then you've got a probability distribution. So that gives us a way of describing probability distribution. This is a very, very simple way. Now, if we, so in quantum field theory, time is continuous, and what they do is they basically say, so S is the state here, H is the Hamiltonian, so it's basically, it's an operator on the state, which gives you the rate of change of the state. So the state here is the probability distribution over the ABM that we're interested in. So we're actually dealing, rather than dealing with just states, we're dealing directly with the probability distribution. And what we're interested in is how does that probability distribution change with time? And so if we can represent, say the model is at H, so if we can represent the model as an operator on a probability distribution that gives you the rate of change of that probability distribution, then we basically got the dynamics. We've got an equation that describes the dynamics, and you can integrate that. It's just an exponential with an operator in it. If you do the integration there, and then we can take that exponential and expand it out. And these terms we can actually compute. And so very briefly, if I can change the slide. Right. So very briefly, so really briefly, this is the way we can describe the Hamiltonian in terms of the action and interaction of agents. So it turns out it's quite simple to think about, because what we want to really think about is in terms of from an agent's point of view. But it turns out that we can actually describe this H in a way that's very natural from the agent's point of view. And once we've done that, then we've got the dynamics of the model, and we can do Bayesian inference. So I actually did this for predator prey. So implemented it. So it was basically a spatial predator prey model. The picture of it is the red dots, the prey, and the blue dots are predator. And the haze behind it is the probability distribution that the data assimilation or the analysis thought for each square, what's the probability that a predator or prey is in that square. And the observations were just noisy, random, incomplete observations of where the predator and prey were. So we're actually only observing 2% of the prey. So actually it's done quite well, given that. And I've also got one with, so I also looked at mutual information. So using this technique, you can see that the mutual information between what the model thought the state was and what the state actually really was, it was going up with time. So that's a good sign that actually it is collecting information from the world or from the observations. So that was what I did with quantum field theory, and so that was like really just very much the beginning of what I think could be, a really interesting approach to dealing with probability distributions over agent-based models. I think it could be expanded in lots of different ways. I'll just mention really briefly some other work that I'm doing in the same domain. So I found also that what I call fermionic ABMs, which is ABMs where the agents can't be in the same state at the same time, there's a way of transposing projecting these ABMs onto a convex polyhedron, and once you've done that, you can do a whole bunch of stuff, like look for the maximum a posteriori, or you can do sampling. So that's what I've been doing in the last few months. Well, I've run out of time, so I should stop.
Thanks very much, Dan. I guess, I mean, you did say, you sort of skipped over a few slides there where you said, this is the model, and now I can do data assimilation. So I think I'd happily give you a couple of minutes if you wanted to say anything about what is probably a very hard part of what you described.
Yeah, I was thinking, like, how am I going to describe this in 10 minutes? Quantum field theory. It usually takes a few years for people to get their head right. I mean, if there's interest, I could go into a bit more detail. If you just want to go for questions.
Yeah, well.
It might be easier just to go to the kind of overall picture. I think I'm not going to be able to teach people quantum field theory in 10 minutes.
Okay, so any questions? If there aren't any questions, then I'll probably resort to saying, well, you could tell us a bit. Oh, Gesine, did you want to ask a question?
I've got a hand. I have to say I'm a little bit baffled, but it sounds all plausible. So for agent-based models, I understand sometimes agents are given sort of characteristics, explanatory variables, like age or gender or what have you.
Yeah.
How easy is that to include in your framework?
Yeah, sure. So I mean that's necessarily a kind of part of it. And so with the predator prey, well, it was super simple. Like the characteristic, you are either a predator or a prey. But yeah, you could also include internal state in the agent. The big limitation of this approach at the moment, which is again something that'd be interesting to look into, is that if as the internal state grows, so let's say, if you say, how many bits or how many bytes of information can you store my internal state in? As that grows, then what would it be? The amount of storage you need to represent the probability distribution goes up exponentially. So so it works really well for agents with very small state. So up to about you know, up to about 4 bytes or something is fine, and then after that, there's a potential of it kind of depends on what your observations are and exactly what your dynamics is. But part of what needs to be done in the future is using approximations. So it's like, right, okay, if the internal state of your agent gets too big, say it's 1K or something, then how can we apply approximations to this probability distribution so that it's tractable, so that we can represent it inside the computer? And this is something I've started thinking about, but yeah, it's early days.
Thank you.
Any other questions? Do you want to say a bit about how the data assimilation part works?
Yeah, I mean, I could go into a bit more detail. Let's see if I can. Where are we? It depends if let's see again. Oops. Oh, I think I've crashed. Oh, no.
Dan has been working with Nick Mallison and I in Nick Mallison in geography, and I don't know. I mean, personally, I hadn't seen something along these lines before, but I have. You know, you can see similarities with the kind of Markov chain approaches, and I appreciate. And there are certainly approaches to dealing with stochastic processes that I'm not really sort of particularly familiar with. So I don't know. I guess I'm wondering if anyone feels that this is, I don't know, is it is it something that's familiar to them that they think they've seen before, or is it like highly novel? And I mean, I think one of the things that is clear is that the way that Dan's been doing it is it kind of allowed us to actually, do the data assimilation in a sort of exact sense, or at least in a computationally exact sense. I think that's fair, isn't it, Dan? For these sorts of models. Sorry, I think Dan is having trouble with you're having trouble.
Yeah, I'm not. Can you still hear me?
Yeah, we can still hear you. So don't worry.
Okay, so my screen is completely frozen, but if you can still hear me, then
I can still see you and everything. So your camera's evidently working. So.
Oh, really?
Yeah.
Oh,
yeah.
Okay, so mine's completely frozen.
Yeah. Oh, sorry. Yeah.
But if I can still talk, then yeah, I can go. Sorry, what was the question? I was
actually pitching a question to the audience to see if anyone had any opinions on any overlaps with things that they might have seen before, and I was saying that one of the things that seemed really novel to us is that even if this is something that is similar to other frameworks that have been developed, the fact is you can do the data assimilation, and in what I said was a kind of numerically exact way, right? Which is something that seems extremely challenging. I don't know if it's worth saying a bit about what data assimilation is. I guess I've just assumed that people would know, but.
Can I just ask, I suppose I'm aware of, the kind of classic Van Kampen style approach of write down a master equation, or, and maybe derive like a Fokker-Planck equation from that or something. And I think at some point you mentioned, Dan, that in the quantum world, you have to deal with the complex variables and all that kind of stuff in order to get your observable probability distribution. But with agent-based models, I guess they're probably a bit more, what's the word, like realist. Maybe you don't have to deal with some of the quantum weirdness. Does the quantum aspect help you over and above using sort of, I guess, more traditional stochastic processes, probability theory tools, like say writing down a master equation or something like that?
Yeah. So there's two sides of the quantum approach, I guess. So the first side is this, the fact that they use complex amplitudes. So the complex amplitudes, I basically just stripped it out from the beginning because I don't think it is useful in the context of ABMs. So if you rework it all the way through without complex amplitudes, then you basically end up with what I had. The second innovation, I guess, from the quantum field theory side of things is just the use of operators. So the idea that the Hamiltonian is an operator. So this idea of creation and annihilation operators, and describing. So these are basically operators that you know that don't commute. And so by using those, and that's basically what that's the useful bit in terms of ABM, is to think about the model as an operator on a probability distribution, where that's made out of or constructed out of creation and annihilation operators, which are these operators that don't commute. So basically, when I was doing the experiment with the predator-prey model, I was really on the computer. It was doing symbolic manipulations of these operators, and that allowed me to.
Oh, I think we've lost Dan. So perhaps his computer has. Oh, Dan, you look like you've gone on mute though. But I guess if you can't see your screen, it's going to be a bit difficult to tell. But hopefully you can hear us. I guess Richard had a question, but I guess there's probably two. Not. I don't know. I mean, you can ask it, and
no, it's all right. It's I think it's broadly consumed by other questions anyway.
Yeah. Okay. What I suggest we do is, given technology problems at Dan's end, let's move on to a final talk, and then if we have a bit of time at the end, we can always. We're nearly at time anyway, but we can always append some questions onto that time if Dan can make his way back. Dan, feel free to reboot if you need to. Okay, our final talk today is going to be from Gesine. Sorry if I've been pronouncing your name wrong. I should have said it. I should have asked. You're currently on mute though. I mean, I know you're getting your things ready, but just in case.
Okay, is this better?
Brilliant, fantastic.
Okay, so when you sent me this email yesterday asking whether I could give a talk, you said a 5-minute talk. So
5 minutes is perfectly fine, because I asked very last minute, so I appreciate that you can do anything. So 5 minutes is fine. Yeah. I mean, I think amongst us, I'm sure there's plenty of scope for discussion.
Yeah, but I mean, these are slides we could talk about for hours on end, I think. So I called it Networks for Social Good. Just try to focus my mind. So the first question is, which networks? So many complex data sets can be usefully represented as networks. So I know there was a sort of agent-based modeling part here, but the one which Michael presented clearly relates to a social network and dynamics on a social network. So relevant networks include social networks. Yeah. So Twitter, we've already heard, other social media. Also, classical social networks are constructed using questionnaires. So asking pupils in a secondary school whom they are friends with, but also whether they smoke, they don't smoke, whether their parents smoke, their parents don't smoke. So these kind of detailed network data. Financial networks, something that I've looked at a little bit. So transaction data, so where you've got well, bank accounts and transactions between bank accounts, for example, but also trade data, so world trade data. So arms trade data, for example. And epidemic networks, we've already heard mentioned, Oliver has worked on that. So we could think of contact networks. So networks, so some networks arise just naturally. When you think of a social network, you say network. But also when you look at financial transactions, they can be usually represented as networks in order to draw conclusions. So it's a data representation angle as well. So what are social good questions in networks, which I could think of? Well, so in social networks, there's easy or sort of things that have been studied is influencing behavior, such as smoking. So a group around Tom Snyder has looked at that in detail. So what is it that drives people to smoke? So teenagers, are they more influenced by their peers smoking, or are they more influenced by their parents smoking or non-smoking? And is there a gender difference? And they found actually there's a gender difference in terms of influence. So this is very detailed stuff which can influence policy. So it was found that sort of in women, there's more of a peer influence than in men. So if you had to target a campaign, you might want to target it differently depending on adolescent women or adolescent men. Opinion formation, Michael already talked about. So how do people reach consensus? So there are mathematical models for that. So Markov chain models, there are ideal world models, but there's also the whole age-based modeling framework. How is opinion formed? So a doctoral student of mine looked at if you inject new information, sometimes in the process on the network, at what time should you inject the information? So depending on the time when you inject it in the formation process, well, actually, as Michael very nicely illustrated, can have very different effects. So if you introduce bots very late in the game, you might want to have more aggressive bots than if you introduce them early in the game and try to have them very low level. Social organization. So I'm thinking of David Sumter, who done terrific work on animal organization. So how do groups of animals or groups of social creatures organize themselves in order to achieve something? So this is also, could even think about COVID. So social organization is certainly going to change or has changed during lockdown. So very, very different mechanisms arise. So what are these mechanisms and can we influence them? Do we want to influence them? Financial networks. So one angle on financial networks is modern slavery, because some forms of modern slavery include transferring money. For example, slaves have to transfer their social security, so social benefit payments to their slave master. That's a typical pattern so as soon as they receive it. So this is something which you can in principle detect in a bank network and financial networks and banks. So it's not usually detected because banks look at, often look at high volume trades, so the big fish, whereas this is very low level, but there should be a signature in financial transaction networks. And so I've talked to that about a few people, and I think we might be able to do something about that. Fraud detection is something that I have actually worked with Accenture, or anomaly detection, I should say, in networks. So financial fraud affects people sort of on a very clear basis. So if it's not all financial networks, but so if your account gets hacked and something malicious is happening, that's clear infringement. Trade networks, fairness in trade. So how can we ensure, or how can we understand the trade flows and how trade flows might affect different types of countries differently? And so imposition on trade regulations, for example, forming trade clusters, that might be very interesting in Britain in the years to come, dare I say. Epidemic networks, of course, spread of disease is a clear question. So these are social goods questions. There are many more. We've heard many more today. So mathematical questions. I mean, why would we want to have this as the Isaac Newton Institute? Because, well, it's a mathematical research institute, and there are many mathematical questions to address. So, so I come from a applied probability viewpoint. So I do look at models of networks quite a bit. And so I found the modeling discussion quite interesting about models being useful, but it's clearly so for me, so models can be useful for sometimes for good prediction, but also to understand the behavior of these systems. So what would be the typical behavior? How can we assess deviation from typical behavior unless we know what typical behavior is? And so mathematically, these network models often have intractable probability distributions. So they impose some kind of dynamics like in agent-based models. And then, yes, in principle, you can divide by the normalizing constant so that everything sums up to 1, but the normalizing constant you just can't calculate. And when the normalizing constant depends on the parameters you want to estimate, that's a hard question. But it's important to understand the behavior of these models. For example, with respect to just simple network statistics, what is the typical degree? What is the typical number of friends? So what should we expect to see? Also, with respect to clustering, so community detection algorithms, which you might have heard of, they are very friendly. So you ask them, so you put in a network and they give you a clustering, but they don't tell you whether the clustering is actually significant. So if you put in a completely random graph called Bernoulli random graph, but all the edges are independent, any clustering, network clustering algorithm, community detection algorithm will give you an output. But is it actually meaningful? So how do you assess whether the output is meaningful? That's unsolved. So also understand, so there was a bit of a shock a couple of years ago when it was found that even in these Bernoulli random graphs, a standard measure for assessing community strengths, which is called modularity, can achieve any value up to one, indicating very clear community structure, just purely due to randomness, and that's a probabilistic result. Stochastic dynamics on networks, so that goes into all the opinion information spread on networks. But also networks themselves might change, might evolve. So I think there are lots of scope for probability, for probability angle here. Statistics, yeah, obvious question which relates back to what Oliver said, parameter estimation, and then also assessing goodness of fit in models when the likelihood might not be tractable. For example, you don't have a normalizing constant. So there are some ideas out there, but so in the most standard social network models, the exponential random graph model, this is still not solved. So people have ideas what to do, but there's no nice framework. Possibly also the model is not well enough phrased, because there's the parameter estimation is there are regions where the parameters are not unique, so not identifiable, which is also a bit of a shock to the system. And that is, people only are starting to understand that. And then statistical significance of community detection outputs, it's a problem which is still not solved. And something that I've started to look at more seriously is network time series models. So models for time series, so standard models, if you've done a time series course, you have a stationary time series, and then you try to model the trend and sort of maybe the volatility, so the spread, and you can make predictions. But when you look at time series of networks, they're usually not stationary, because we're interested in them because something changes. But there should be some patterns, and people are starting to look into network time series models, but the standard, so far, they analyze them as if they were stationary networks, but that can't be right. So there's a lot more to think about. So that's could be a whole program at the Newton in itself, but there's clearly scope. And then statistical machine learning, which you heard a little bit about, and especially in the discussion. So we need actually theoretical guarantees for efficient methods. And so efficient methods for training network models means basically parameter estimation, but using neural networks, testing goodness of fit of a model, and also generating samples from networks. So that has to do, for example, with privacy. So you want to, if you've got sensitive private data, such as financial transaction data, you don't want to analyze them. You can't make them public. You can't make the data set public, but you want to have a data set which looks like it in a sensible way, in which other people, so researchers can then analyze and try to cut their teeth out. So there's so that's also another machine learning problem, and the theoretical guarantees are wide open. So it's, was it Richard who said that, you have, you run, and Oliver also made that point, and David made that point. So if you run a black box, you don't know what's happening. So transparency of black box in this area. And then there are, of course, other related mathematical areas I don't know so much about. Well, combinatorics is an obvious one. So how do we understand the combinatorics of these models? Dynamical systems, which I think, so John is I think is on the case, and other people. So opinion formation is an example of a dynamical system. So here we would probably have to think of stochastic dynamical systems on networks. So how do they, so when you've got a dynamical system, but you've got a network dynamic as well. So how do these interact? So it really will depend on the different timescales at which these happen. And then mathematical physics. So I was not actually thinking about quantum field theory when I wrote that. maybe I could have done. I was just more thinking of physics models for complex particle systems. So particle systems which are not like the Ising model. So yeah, even the Ising model on a graph. So if you've got just spin up, spin down dynamics, but on a graph. So we understand that in the high temperature regime when it's almost random, but there are many regimes where there are lots of open questions, and also depending on the type of underlying graph. And so these mathematical physics sessions, they could then also feed back into opinion formation models, for example. If you think of the voter model being a simple model for opinion formation, but actually coming back from mathematical physics. So there's a whole stream. And so these were my thoughts. So that's what I wanted to flag, some ideas which I thought we could look at in the program. Thank you.
Thank you very much. Does anyone want to ask any questions?
Yeah, I was just wondering how much you've done on the simulating dynamics on networks side, as opposed to say like analyzing network structure.
So I haven't done much simulating. So I've done a lot of work on epidemic modeling. So SIR networks, including COVID modeling. But I've also had the student, and she looked at opinion formation on networks. So we had an opinion process running on networks. So those are the two areas where I've done work.
Yeah.
I've done a lot of work on protein interaction networks, but I thought that that's really twice removed from social good, perhaps.
I mean, because it strikes me, so I'm like, I know enough to make stuff go, but there's a lot of technical, interesting challenges around like, simulating processes on really large networks. Like we're trying to run stochastic epidemic simulations with many different types of state, like SEIR plus with, quarantine and contact tracing, all these things on 5 million individuals, this kind of stuff. And just efficiently doing that, seems like there's a lot of open problems mathematically in terms of how to, do algorithms for large scale simulations on networks. So I mean, yeah, like I agree that a lot of those topics that you talked about could be whole workshops in and of themselves. I mean, another thing too that comes up, I'm just kind of again talking out loud, but I mean, something that we've encountered, right, is having to deal with like non-Markovian type processes on networks as well. So I mean, the classic epidemic stuff like SIR model, you assume Markovian processes.
I don't actually in my work, so that's sort of my unique selling point, as it were, that with my coworkers, so with Andrew Barber, so we don't have any Markovian structure. We've got a point process.
Okay.
So the Markovian case is a special case, but no, I completely agree that Markovian is not adequate really for epidemic modeling.
Yeah, well, I mean, yeah, when you do things like, okay, I mean, there's a time to recovery, or there's a time that you're going to put people into quarantine. and it's all very well to say, yeah, the mean time in quarantine is this, but there are some people getting out of quarantine within a few minutes, and it's not, like it's not realistic. But actually, I mean, because then doing like the stochastic simulation of non-Markovian stuff on networks, I mean, these are all like annoying questions that government people ask us to implement, and they're very difficult and technical. And so there's, I mean, it seems like there's a lot of potential for those kind of things, just in terms of, people don't want your vanilla, SIR on a network. They want all kinds of different processes and these kind of things. And so that's definitely pushed me beyond my comfort zone in terms of implementing things. So I could think of a million things along those lines that would be at least open problems to me. Maybe other people already know how to solve them.
Yeah, but see, in the epidemic modeling, so the complex part is the infection mechanism, right?
Yep.
So that's why you don't want to have Markovian structure in there. But so what we do, we just model the whole point process of individuals and when they get infected. And then what happens when they get infected, we assume that is then no longer dependent on the infection process. So all kinds of things can happen. So they might be in isolation, which might, so that would affect the infectious rate. That's true. But so you can, and then they will recover at some point. So we try to decouple that and focus mostly on the infection mechanism, which is of course dependent. And so the individuals have a sort of contribute to the infectiousness in the population at rates which are time dependent, but also could depend on other things. Could be stated.
Yeah, and another thing, I mean, sort of along those lines in terms of infection mechanism. So, I mean, something policymakers and stuff are interested in, obviously, is things like, what if we shut down schools but keep businesses open, or we, all these kind of things. And so, I mean, the way that we have been doing it is we actually have, so not just one type of node, we actually have two types of nodes. So we have individuals and we have group type nodes, representing contexts like, schools, communities, workplaces, and then thinking about, how to define the infection process, basically the kind of mixing processes within group nodes and this kind of thing. I mean, there's a million questions.
Our main focus is sort of the household structure. So we've got a social network, but then the spread within households is very different. And because of the incidence rate, we find, especially here in the UK, we cannot ignore that.
Yeah, no, I mean.
So the within household spread.
Absolutely.
Yeah, it's a big thing. Sort of going out of
I think David has got a question as well. So it might be worth. David, did you want to ask?
Yeah, I suppose I was just trying to get into the practicality of it, thinking about the workshop. What would be for you the biggest thing that you'd like to see into? I mean, I think it's very interesting. I think some of the results I find very interesting is this, as you mentioned, the community dynamics thing, where you show that you think you're measuring community dynamics, but you're just measuring something random. I think that's very interesting. And then, of course, there's all these things on networks. But what would you like to really get into the social good conference or workshop program?
Of these, well, I certainly think social networks should be there. So I think that's, and I would like to include people from social network analysis. So people like Christa Geil, Tom Snyders, Johan Koskinen, so people who really look at these intrinsic models, because they have a lot of insight between statistics and application area. But then it would also be good to have people on the boundary from probability and statistics. So I haven't actually thought much about workshops. So there are different ways of structurizing them. So one would be to have a sort of focus on one particular application area and then try to tackle that from all three sides. Or there could be the sort of the cross-cutting. So all three sides, meaning so mathematics, statistics, and applications, so social science implications. But there would be other things like foundations of inference, but that might not be. So it would be good to have a program which is coherent in a way that people who stay for the 6 months will want to attend every single workshop.
I don't know if you have any opinions on whether whether we just want to kind of embed networks in everything as much as possible, because I mean, in a sense, many things link with agent-based models, and many agent-based models are, kind of linked with like dynamical processes on networks, or whether we want to carve out like a sort of, whether we want to carve out a separate like part to the program where we say, we're tackling these things, and then like currently in the draft we've been talking about puzzles, so perhaps it's the puzzle of networks, right? So I don't know, do you have any opinions, on what you'd prefer? I can imagine what you might answer actually, but yeah,
it depends a little bit on the mix of people that will be coming. So if we think so, it's sort of so if you think it's the predominantly AGM agent-based model people, then we might want to have a sort of a specific workshop on networks. But if it's a mix, then I think it would be very interesting to combine the two. For example, in opinion formation, so if we had themed days, one on opinion formation, we can look at network models as well as agent-based models, compare the results. Similarly with COVID modeling, I don't know whether that's what we want to do, but that's actually something that we were trying to do here in the UK, to look at, compare theoretical results with simulation results as well.
I wonder with the COVID angle whether, because what's come up a lot is the kind of learnings that people have had from doing this, and particularly probably many people being much closer to policy makers than they would have been otherwise, perhaps. It might be interesting to, like, rather than it being specifically about pandemic modeling, because obviously the INI, well, not obviously, but the INI have been doing, do have a program on that at the moment. So it might be more to do with, look, these are real important outputs that, or important sort of things that have happened to people who have been involved in that. Thinking about the, for example, stuff that Oliver mentioned, and it also got mentioned before about, you get told to Jess Enright mentioned this, you work with someone like that, they say we want this, so you have to do it, even if you don't really necessarily believe in it. And, Oliver's kind of echoed that. So yeah, it might be nice to just take those things and say, look, from the whole COVID epidemic, these have been crystallized as really important issues that have occurred, and this is, and they're going to feature in the program. But no, your point about the mix of how we mix the people, that I think that's a good way to think about it. Any other, Richard, did you want to ask something?
Yeah, I think in terms of creating the program, a very important question is what you as a network researcher feel that you can get out of it, because I can see many ways that your presence and the presence of researchers who are interested in this could be very useful. From my perspective, in the sort of animal behavior world, I can say that a lot of the research that gets done on what are called social networks doesn't smell quite right to me. That there's sort of this, I get a sense that a lot of it is sort of finding, like David said, finding communities that are actually just noise, or saying I've inferred a network, but that network has been inferred using what I would consider to be extremely sketchy methods, and then making sort of wild steps beyond that. So I've inferred a network by saying which animals did I see at the same feeder or something, and then I'm going to predict that these dynamics are going to play out, which wouldn't play out if the social network was somewhat different. And so having people who know about networks from a deep theoretical level and a deep statistical level would be very useful. But I'm equally keen that you feel like you're getting something out of it from us as well, that you're not there just to provide information to us, but also to get your research interests addressed.
Yeah. Many networks people have sort of the favorite network area. For example, there are some people who specialize on food webs, hierarchical networks. So I think there's a real benefit, especially if you make it themed. So I've got an interest in opinion formation. So for themed days, it would be interesting to see the results from people who try to tackle the same questions but with other methods. So I think that would be interesting, but it would also be interesting to get input about what the good questions are to attack in the field. How do we build the models? How do we test the models? Because without good application, so it's so when the field, so this sort of physical type network analysis started out 20 years ago. So people thought, oh, we have these models, and yes, one model fits all. We just do general theory, but of course that doesn't work. So devil is in the details. So you have to do model-specific things while still trying to keep general principles in mind. And so I think there could be a lot of benefit for people from networks
to
come to such a workshop. So to attend the program.
Great.
Any other questions? Or questions at Dan, if anyone wanted to, I can see him at least. I mean, so we're a little bit early, but I don't have a problem with wrapping up sooner. We can continue discussion if people want to stick around. Just to say, you know, there's another session next Tuesday where I think we'll probably essentially try to summarize the discussion that's been had and the things that have been kind of pulled together in the proposal. That is on Overleaf. If you don't have a link to that, let me know, and I can share that with you. It should be in Slack. I have shared it with some people, but I think I've reached my limit there. But I think everyone should be able to access it through the link. So yeah, please. I mean, I think also on Monday we're trying to have a conversation about ethics as well. So I think on Monday there might be on Monday afternoon. I think Catherine wants to be involved with that.
Could I was wondering, I don't know Catherine, or she's the only person I don't know here. So could you just say something a little bit about what you do, or please? That would be really useful.
Sure, certainly. So I'm an algebraic group theorist, so my mathematical background is a little bit different, but I come to this through, as John mentioned, the ethics, but more so through social justice. So I do a lot of work in mathematics for social justice. I saw in the proposal you already are talking about the COMPAS data, predictive policing models. So that is my angle here. So when we're talking about usefulness of models, my brain goes to useful to who? As you can imagine, a very useful model to predict crime might be different for the police officers who are working there versus different entities in society. So that's my background, is just doing work. I work in the prison systems as well here in the US, doing work in mathematics for social justice, both how we communicate mathematics to the public to make sure they understand what's going on in our algorithms, and also making sure that we're always being mindful about how we teach mathematics, what we teach in our mathematics, and how we can bring ethics and social justice into it.
Thanks, yeah.
Yeah, maybe could we talk more sooner rather than later, because we're writing a large section in this proposal and none of us are an expert in it, and it sounds like you are. So it might be good if we could get you involved quite quickly. And we don't have to keep everyone else on, but Richard and John and I had a long discussion where we were putting that as a very central problem, but none of us are really experts in it.
I don't know if I consider myself an expert, but I have been doing work on it for some time, and it is something that's very important to me.
Okay. Yeah, no, that would be.
So I guess then is Catherine, are you able to hang on for a few minutes after we finish?
Oh, I'm not going to bed anytime soon, so.
Well, but you might have other things to do, like eat breakfast or get ready for the rest of your day. Yeah.
Yeah. I mean, is it possible to do a quick presentation of what you do?
David's
I'm certainly willing to stay. I mean, I don't know, now we're making you prepare it without any, or could we take a 10-minute break and then have a presentation?
I'm happy to prepare something perhaps briefly on Tuesday, if that would be okay or appropriate.
Tuesday we have, I mean, Tuesday is sort of our last core hours day, although obviously I think we will continue to work on this. So, I mean, I don't want you to feel pressured into doing something. I mean, I think I guess from David's perspective is that we just want to know something that we could perhaps write. I think I would be happy for that if Monday, I mean, we have been talking about having a chat on Monday, I think, right? So, I mean, I would be happy for that to happen on the Monday. And I think that gives us a little bit of time to or, you know, at least we can, you know, we'll have a conversation around ethics. If you have anything that you can have for that, that's fine, but don't worry, please don't feel pressured into doing something if you don't. And I mean, yeah, I'd be happy to have that discussion then. I think it gives us a bit of time. I appreciate that the more the better, but I think what we're hearing is let's let's not rush it. So
I'm happy to chat. Yeah.
Could you post your paper or have you got some written things or something you could post in the
or even things that you're aware of that people have done that might be worth us considering? Yeah,
sure, I can put them in the Slack place if that's fine.
Sure,
absolutely.
Yeah, so I don't want to keep anyone longer than they need to be. Thank you everyone for coming. Thank you for all the speakers. I think today was really interesting. We hadn't originally planned to have some talks, and the INI really encouraged us to, and I'm glad they did, because I thought that was a really good way to stimulate discussion. And it was really nice to see the crossovers between things that we've discussed already and what people are thinking, and there really does seem to be like commonalities in the issues that people are facing. So it's really good to hear. Like I said, yeah, please, I mean, we have we have the Slack. I appreciate we have quite a lot of things going on in order ways to engage, so I'm sorry if that's overwhelming. And we do have the Slack channel is probably a fairly easy way to send some messages through that. I guess the other thing that we've been doing is, although I haven't been doing it today, I confess, we have something called Sococo. Catherine, I don't think I've signed you up yet to it, but so that's another way. That's just a kind of place where we can meet, and if you want to come and chat to us, if you have 10 minutes, we should be there. And it's fairly easy to just it's a bit like an office where you can just drop in and see people. We are currently just finalizing arrangements for that discussion about ethics, so I will send around an announcement about that, and I'll have a quick look if anyone else wants to say anything before we break. I'll probably
John,
go on.
I'll just say, I mean, a bit about the Overleaf document. I mean, because most people, of course, have not been involved in our discussions, that we've been sort of winding our way to a position of writing in the form largely of a series of easily described mathematical and social problems. You'll see a couple have already been written in there if you go there. The list that we've written is sort of indicative and where we think people might have stuff to say, but it just doesn't have to be exhaustive. If you think there's a nicely, concisely describable social or mathematical problem that would fit in there, then by all means write a paragraph about it, or even just a couple of bullet points about the sort of things that would be useful to say. And of course, come and ping us for discussions about exactly how you can contribute or what you might like to contribute beyond that, or if anything's unclear about, for example, the format of the proposal or how you can get involved.
Okay, thanks.
Sorry, I still wasn't sure. Where are we going to? Now I feel like I'm putting Catherine, but I'm very keen to get your input on this fairness puzzle thing sooner rather than later. Or are we? Now
I'm happy to hang out for 5-10 minutes, Catherine. If you can, that would be fantastic. If you can't, don't worry. And yeah, there's no pressure there. And other people, if you want to go, feel free to slip away or stick around if you want to. So, but other than that, let's close it there and say thanks for today. Like I say, I'll certainly hang around for a sec if we want to have a sort of continued discussion, and if other people want to, please feel free to.
Thank you.
Cool, thank you.
Cheers.
Okay. Thanks, John. I'm afraid I have to go because I've got to eat something before my next meeting.
Yeah, I probably should do that.
That's okay. You too. Yeah.
I'm happy. Catherine.
I'm very keen on this because I feel like I'm not really, I mean, I know a bit about this, but I don't feel like I'm the expert. I mean, nobody's the expert, but I certainly haven't worked with any prison systems. So could we have a 5-minute break, Catherine, and then just come back to this discussion? Is that okay?
Sounds great. That sounds great.
Great.